Hi, my name is Miriam Lowery, and this is Lab 1, Constant Velocity for Physics 2211. The purpose of this lab is to apply Newton's second law of motion to the real world by observing an object's motion and comparing that recorded data to a computational model of the expected movement of the object in relation to time. Some important definitions. The system is the object being studied, which in this case is a ball. The surroundings are all of the variables that could potentially influence the properties of the system, which in this case are the desk, room, etc. A force is a push or pull exerted on the system by the surroundings. Velocity is a vector describing the change in position of the object over the given time interval, measured in meters per second. Acceleration is a change in the speed of the system, or the change in velocity of an object, over the given time interval, which is measured in meters per second, or meters per second squared. Newton's laws of motion are included in this lab. Newton's first law says that an object's motion will remain constant unless acted on by an outside force. Newton's second law says that the motion of an object is dependent on the net force acting on the object as well as the mass of the object. Net force is equal to mass times acceleration. From this we can derive the velocity update formula, which says that final velocity is equal to initial velocity plus net force divided by mass times change in time. The experimental design includes the system, a lacrosse ball, which is 0.142 kilograms, and the surroundings, including a desk which is 4 feet or 1.22 meters long. The procedure is the following. Record the movement of the ball traveling across the desk at a constant velocity. Analyze the video using the tracker software. Edit the given GlowScript starter code to create a computational model accurate to the system. Create position versus time and velocity versus time graphs for both the observed and the computational model. Compare the results. Here's the tracker video, which shows the ball traveling across the desk at a relatively constant velocity. The video is trimmed at the beginning and to eliminate acceleration at the start and deceleration at the end. Due to the presence of outside forces, including friction and gravity, the velocity does not remain exactly constant, as is seen in the velocity versus time graph, which has staggering points when comparing the velocity over the time interval. Still, the velocity is relatively constant as seen in the position versus time graph, which has nearly constant slope over the time interval. Motion in the z direction, towards or away from camera, may also present an issue as it could affect the observed velocity in the x-plane. Now to the computational model. The computational model assumes that there is an f-net of 0, resulting in constant velocity represented by a constant slope in the position versus time plot. This constant velocity is represented by a slope of 0 in the velocity versus time graph, indicating that in a perfect system, no acceleration would occur. This constant velocity can be seen in the data points output by the GlowScript code. When comparing the two models, the slope is nearly the same for the first few frames of the ball's motion. But towards the end of the motion, the recorded motion began to drift away from the constant slope of the computational model. The final observed position is approximately 0.0645 meters away from the predicted position in the positive x direction. What could have caused this error? The difference in slope indicates that the ball was observed traveling at a higher velocity than was predicted by the computational model. This variation may have been caused by a tilt in the surface across which the ball traveled, causing the ball to accelerate. The length of the reference point used in tracker may not be precise. Computational model does not account for friction force and therefore could cause some inaccuracy. What if the axis were flipped? If the ball traveled in the negative x direction, the speed of the ball would remain the same since speed is scalar, but the velocity will be affected since it's a vector. When filming the video, the axis was set. I moved the ball in the positive x direction, allowing my data to move in the positive y direction with a positive slope. If the axis is flipped, the ball that was once moving to the right will now move to the left, also known as the negative x direction, creating a negative slope in the negative y direction, as seen in the given graphs. What does it mean? Because the system moves at a constant velocity, we know the net force is equal to 0. Still, it's impossible to determine all the forces present. Within the x-axis of the experiment, the forces we are aware of are the force applied by my hand, which starts the motion, and the friction force, which acts against this motion in the negative x direction. Within the y-axis of the experiment, the gravitational force is acting in the negative y direction with a force equal to the mass of the ball times the gravity of the Earth. Combating this force is the normal force acting in the positive y direction. In conclusion, in this experiment we are able to create and analyze the motion of a lacrosse ball in the positive x direction using tracker and compare that positioning model to a computational model created in GloScript. The observed position model is nearly accurate in comparison to the computational model as the ball moves at a near constant velocity with no apparent outside interactions. This demonstrates and helps us to understand Newton's second law of motion.